We just learned how to extract data from a motion observation recorded on video. Now let's discuss how to construct a model both to understand and to predict that motion. We will focus here on the key steps needed to construct a computer model. Once again, we encourage you to work through these steps on your own because it's good practice for the labs. It's especially important if you are new to writing computer code. You can practice here many programming ideas that will be needed for the labs. Now, if you're a little nervous about writing code, we encourage you to be bold and to dive right in. After some practice, you will do just fine. If you're skeptical about the value of writing code in an introductory physics class, then you should know that theory and experiment, the two major ways of doing business in science and engineering, are now, in the 21st century, joined by a third major and equally important way, and that is computational modeling. Now, for newcomers, skeptics, and everyone else, we invite you to watch a pep talk on coding and computing by some people you may recognize. Now, before we get into details, let's briefly remind ourselves where model construction fits in the way we think about doing physics. What we'll talk about today fits squarely in the realm of developing explanations. We will discuss how motion concepts and Newton's second law can be used to build our model. We'll start with launching VIDLE, the software application that provides the setting where we will write and run our computer codes. Now, from VIDLE, we'll open the Python program called lab1start.py. You can download this program by clicking on the link, which should pop up now. The program will open in a code window, which is where we'll make changes. And it should look something like this. Now, you may, if you choose, begin from this program and make changes as needed when you develop your computer model for Lab 1. For every lab, you will always be provided a starter program, so in this class, it won't be necessary to write a computer program from scratch. The starter programs should always run with no errors, so it's a good idea to check that first. This is how the Lab 1 starter program should look when you first run it. But let me emphasize, starter programs do not contain the correct physics, so we have to make changes to put in the right physics here. Now, if you're new to programming, then here's some good advice. First, it's a good idea to make and test only a few changes at a time. Moreover, it's a good idea to rename and to save periodically. That way, if you make a mistake in the code you can't track down easily, you can always go back to your last working copy instead of starting from the very beginning. Now, let's take a look at the Lab 1 starter program, which runs in sequence beginning from top and moving downward. Now, we will be switching between the VIDLE code window and lecture slides showing parts of the code in larger font. There are parts of the program that are important, but we almost never need to pay attention to. We can see this at the very top. Let's notice here the very first line that begins with a hashtag symbol. Lines that begin with this are typically comments, which the computer ignores all text after the leading hashtag in the line. Comments provide useful notes to help us understand what's happening in the code. Now, moving downward, we see another group of lines, and these lines won't need to be changed either, at least for the first lab. However, we need to talk about these lines of code because they provide the initial setup for different representations of the motion we're modeling. A graph window is initialized so that we can plot motion quantities. A second window is created to show a visualization of the motion determined by the motion physics we put into our model. The code creates a simulated object, here a ball, that will show in the visualization window the motion we predict. If we get the physics right, the motion of the simulated object should look like the motion of the real object we observed and captured on video. We also include code that sets up a track that will be left behind the simulated object as it moves. And finally, we include a marker which shows us where the origin is in the visualization window. Now, when the visualization window first appears, the orientation is such that the positive x-axis points to the right, the positive y-axis points toward the top, and the z-axis is positive out of the screen. However, we can use our mouse in the visualization window by left-clicking and dragging to rotate and to change the orientation of the visualization window while or after the program runs. The next set of lines are where the physics begins. This is the first of several places in the program where we'll typically need to add or to modify code. These places are indicated by comments that begin with the words, "edit this." Now, here, to predict motion, we'll typically need to specify the mass of our system, the soccer ball. So we will put in that information, which we can get by measuring the soccer ball's mass or by looking up the mass of a standard soccer ball in appropriate units. Here, we're using SI units. Now, for comparison, we could write a similar statement in algebraic form. For example, the mass m ball equals 0.45 kilograms. The algebra statement looks very similar to the code statement, but there is a very big distinction. The algebra statement is an equation where the left-hand side and the right-hand side of the equations are, well, equal, which means, for example, if the equation is written in reverse, it means the same thing. In the code, by contrast, the statement ball.m equals 0.45 is not an equation. It's something we call an assignment statement, meaning that when the program executes this line of code, then the quantity on the right-hand side, 0.45, is assigned to the variable on the left-hand side. So, for example, if we wrote this in reverse, this is not a valid assignment statement and would cause an error. So we need to be a little bit careful here. Now, to predict motion, we also need to specify where the object is at the start of the prediction and how it's moving. Recall that we already estimated both the initial position and the initial velocity from the video we analyzed. So we can insert that information here using assignment statements, in which case we have to ensure that we use the correct syntax for vector assignment statements, since the quantities that we're talking about here, the initial position vector and the initial velocity vector, need to be specified as vectors. Now, also note that the ball's observation time is something we need to pay attention to. So this is something we also can insert if necessary. Again, we need to make sure that all these quantities are in the SI units that we decided at the beginning to use. There's one more quantity that's worth looking at every time we construct a computer model, the time step, delta t. Recall that when we're predicting motion under Newton's second law, we typically will predict only a small time into the future. that small time is determined by delta t. Small means, as a rule of thumb, that delta t needs to be set to a time interval that's much less than the typical time scale of the motion we're observing. So recall that when we observed the ball's motion, we watched it for about 1 second. So we want to choose delta t much smaller than this, say 100 times smaller, like we have here. There are more precise ways to specify delta t, but this choice is plenty good for now. One more quick point. It isn't necessary to set delta t to the time interval between frames in our video observation. Right now, right below this assignment statement for delta t, you will see a collection of lines that begin with the hashtag symbol and have the word optional at the beginning. We'll discuss these in the next lecture. We can safely ignore for now. Now we come to the actual part of the code where we will apply Newton's second law. We'll need to do so repeatedly, and we can do this using the while loop, which starts with a line that begins with the word while and includes a set of indented lines below. The loop ends with the last indented line. For this particular code, in this particular loop, the first line in the loop tells us that while the time t is less than a certain limiting value, Newton's second law will be applied repeatedly. Now, a good choice for that limiting value is the final observation time from our video analysis. So let's go ahead and insert that here. So while the time t is less than 0.734 seconds, all indented lines below the first line will execute repeatedly. Now let's look at the place in the code where we put in Newton's second law. We're skipping a few lines of code to do this. Don't worry. We'll back up in a moment. Here's what we wrote earlier for Newton's second law in algebraic form. This doesn't match the line of code we have here, which does not correctly express Newton's second law in its most general form. We want it in most general form so that later, if we need to use this code to solve another motion problem, we'll be able to start from the correct place. So let's modify this line of code so that Newton's second law is just as general as in the algebraic equation. What would that look like? Here's how to write the code correctly. Notice the correct code still looks a bit different from the algebraic equation. The code appears to have the same ball velocity on both the left-hand side and the right-hand side. Here again, we run into the difference between an equation and an assignment statement. This line of code says that we take the original value of the ball's velocity. We take and add to that the change in the ball's velocity, which from Newton's second law is F net over m times delta t. And we assign the sum, a new value, to the variable which contains the ball's velocity. We say that the variable ball.vel is updated. It's updated with a new prediction of the ball's velocity a small time delta t later. Now we need to do the same thing when we're trying to predict a new position. Recall that in algebraic form, the position update is written like this, which again doesn't match the code, line of code. Once again, we need to fix the code. What would the correct line of code look like? Here it is. We say that the variable ball.pause is updated. That is, we're making a new prediction of the ball's position a small time delta t later. We've got one we can also understand how time advances. Every pass through the loop, the time is updated, advanced by an amount, delta t. We've got one last piece to put in our model, and it's a big piece. We have Newton's second law written down. However, we didn't specifically say what F net is. That is, what are the total interactions acting on our object. We need to do this. And we need to do this to model the interactions in a way that fits our observation of constant velocity, motion in the same direction at the same speed. How can we do this? How can we choose F net to make this happen? Here's a hint. Take a look at Newton's second law. From Newton's second law, the only way to get the velocity to be constant is to make sure that this term in the second on the right hand, the second term on the right-hand side of the assignment statement is equal to 0. Since delta t is not equal to 0, that means we have to set the vector net force equal to 0. This is the correct syntax to do so in the assignment statement. Now let's run our code and see what our predicted motion of the ball looks like. By eye, this looks similar to the observed motion we saw earlier in the video that we analyzed. Now we can make this comparison more quantitative, but we'll save that topic for our next video lecture.